Hello students, I want to make a quick video about solution formation and what's happening at the molecular level. So we talked about this example briefly in class. We have the sodium chloride crystal here, and this is right when we've added it to water, and it's going to dissolve and dissociate. So when that happens, there are some interactions that break. Those include the ionic bonds between the sodium and chloride ions and the hydrogen bonds between some of the water molecules. The interactions that form will be our ion dipole interactions between water molecules that surround each of those ions. Of these forces, the ionic bonds are the strongest, and therefore the strength of the ionic bond is the first and primary determinant of whether this process will be endo or exothermic. Of course, when you're breaking bonds, it requires energy. And so that process of breaking the ionic bond to dissociate the ions will be endothermic and require energy. And the same is true for breaking the hydrogen bonds. The ion dipole forces that form are going to be exothermic because we're forming that new interaction. We're making something that's more stable. So the sum of all three types of forces is going to determine whether the overall process of solvation is endo or exothermic. The entropy of the system will increase because the ions will no longer be constrained to that crystal lattice structure, and they will be moving around within the solution. So when a solid dissolves into solution, as I mentioned in class, we're talking just about aqueous solutions. We need to think about all of the interactions that are taking place. We have ion-ion interactions, that's the ionic bond. We have solvent-solvent interactions, that's the hydrogen bonds. And then we have ion-solvent interactions, and that's our ion dipole forces. I've color-coded these in blue to indicate that they are endothermic or require energy, and red to indicate that it is exothermic or releases energy. So for example, for sodium chloride, it requires a certain amount of energy to break our hydrogen bonds, a certain amount of energy to break the ionic bonds. That's what we see here. And then there's a certain amount of energy released when the new ion dipole forces form. And in this case, that means the sum of these bonds that have to break is greater than the energy that's released when the new bonds formed. And overall, the delta H for the process of solution or solvation is going to be positive. It's an endothermic process. That means if we were holding on to this beaker, it would feel cold. That's a sign that it's absorbing heat from the surroundings, where your hand is the surroundings. This is one example, and salts can actually have a variety of different delta H of solvations or delta H of solution. For example, a typical hot pack will contain calcium chloride. This is very exothermic when it dissolves. It'll have the solid on one side and water on the other, and then you squeeze the two parts together and shake it up, and it gets very hot. And that's because calcium chloride, the delta H of solution, is very negative, negative 80 kilojoules per mole. It's very exothermic. A cold pack is usually made from ammonium nitrate, and this is very endothermic. It has this positive delta H of solution. The overall delta H of solution will vary depending on the lattice energy or how strong that ionic bond is. Also, the ion dipole forces that are formed make a pretty big difference. Those are the two largest types of forces that we deal with in this situation. Now, here's the question. How is it possible that if it has a positive delta H of solution, that it's soluble at all? Shouldn't it be insoluble if it's endothermic? And this actually highlights the difference between free energy and enthalpy. So an endothermic process means it has a positive delta H, and a spontaneous process means it has a negative delta G. So if something dissolves, it means our delta G has to be negative. The fact that it dissolves indicates that that's happening spontaneously at whatever temperature we're talking about. And there's two factors that are going to play into this. So we have our delta H, and to help us get our negative delta G, it's favorable when our delta H is negative, or when we have an exothermic process. That will be more favorable than an endothermic process. And likewise, it's favorable because of this negative sign here. It's favorable if our delta S is positive. So we end up with more entropy at the end than we had at the beginning. And we said for dissolving a salt in water, it's generally always a positive delta S because those ions are coming from the crystal lattice and going out into the solution. And so we have this favorable piece with the entropy, and we have an unfavorable piece for our NaCl that was endothermic with our positive delta H. So when is it going to be spontaneous? It turns out if we up the temperature, we're going to magnify the impact of the entropy. And so at higher temperatures, most salts will be more soluble because the entropy term gets magnified. And in fact, when we have an endothermic process like this that is also spontaneous, we say that it is driven by entropy because it's this entropy term that makes it happen, that switches it over from being non-spontaneous to spontaneous. Our delta S of solution is usually positive when we're dissolving the salts. Our delta H can be positive or negative depending on whether it's an endothermic or an exothermic reaction. If the delta H is greater than 0, if it's endothermic, then those compounds tend to be insoluble. But sometimes they are soluble because the entropy term is big enough that it can overcome that unfavorable enthalpy term. So, for example, if we dissolve a certain salt in water and the solution gets cold, is the process driven by enthalpy or entropy? And when we say driven by, what we're meaning is which of these is contributing more to the spontaneity, that sign of delta G. And if we know it's getting cold, that means our enthalpy is positive. It's an endothermic reaction, and that is unfavorable. So in this case, this is driven by entropy because entropy is able to overcome the unfavorable enthalpy of the endothermic reaction. To summarize, go ahead and take a minute to describe in your own words the process of solution formation in terms of the energy that's associated with intermolecular forces. There's 3 different kinds of things that are happening: breaking the ionic bonds, breaking hydrogen bonds, and then forming ion dipole forces. Which of those are endothermic, which are exothermic, and how would you be able to tell whether the overall process is endo or exothermic? And then finally, how can you tell whether the overall process is spontaneous? And sometimes it will be spontaneous at high temperatures, but not low temperatures, or vice versa. So that's the end of our discussion of the process of solution formation. I hope this is helpful and that you have a good day.